Hello, Honors Chem students. This is Mr. Keister here with you again today. This is the video for Monday, September 21st, 2020, which is our scheduled, 22nd day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order of those lessons will remain the same regardless. So let's take a look at the do-nows and see what our schedule is for today. So today is our third scheduled e-learning day, so everyone will be at home today, and you'll be all learning the lesson then from this video. These were handed out yesterday, were handed out Friday, so that you could have those in hand with you today in order to do today's homework. So those are discussion activity 2.1 part B, page 36. And the 2.1b handout over the kinetic molecular theory, or KMT as we call it, which was page 37. From Friday, you picked up the new calendar, and you picked up the lab activity 2.1 part A and the handout for that part A, which is page 35. I want to let you know that your second exam, exam 1-2, I am almost done with them, and I have several students though who haven't taken it yet, and so I probably won't hand those back until tomorrow or Wednesday based on when they take those. But I'm almost done with them, and I should finish them today. So today in class, we're going to go over lab activity 2.1 part A. There'll be 3 demos that we're going to look at in the back here in just a minute, and from them determine some behaviors of gas and liquid particles. Now, you are to watch one more video, Eureka 19, for tomorrow, and finish answering the questions in parts 2, 3, and 4. On this activity part 2.1 part A. The video link for this last video is accessed through my Canvas calendar where the other 3 videos were already located. I also have the link right here if you want to click on it from there if you pull this document up in Canvas. Additional homework for tomorrow, you're to read the instructions at the top of discussion activity 2.1 part B. And using the handout that you already have as your guide, complete questions 1 and 2 only for tomorrow. So that is your homework for tomorrow. Getting back to the videos, if you have not watched videos 16, 17, and 18, they're Eureka. They're cute. They're a little corny, but they're cute, and they're also very good. They explain things in a very simple way, which I've in regards to solid, liquid, and gas behavior. We're going to go over that again, liquids and gases today. If you have not watched those 3 videos, which you were to do for today, make sure you watch them when you watch this 4th one, number 19. All of them are maybe between 4 and 5 minutes long in length. They're not that long. Like I said, they're somewhat corny and a little bit entertaining, but also very good. So that is our schedule for today. So let's head back. You should have lab activity 2.1 part A, page 34 in hand. And I'm going to head back to the lab area and we'll do the demos. So let me unplug here and we will head back there. All right. So let's see here. Where do I want to set this up so we can see? Oh, that looks pretty good. There we go. All right. Yeah, looks good. All right. So let's see. First up on the list. So we're on lab activity 2.1 part A, states of matter. Part 1, of course, was your homework that was assigned last Friday. You were to watch the 3 short Eureka videos, 16, 17, and 18, that were in Canvas on the calendar, and read in your online textbook, Chapter 3, Section 3.3, on the 3 states of matter, and read the Lab Activity 2.1a handout, Part 1 only. On the back of this handout, you were to write down from all those readings. On the back of this handout, you will write down a few key points about each phase of matter, solid, liquid, gas, and illustrate each with a particle diagram. So basically then, you were to have this done right here. All right, so as you can see from the videos and from the handout, you were to write down, answer the questions here in the little data table and draw a particle diagram of each of the three states of matter, which we have looked at before. So this should have been a little bit reviewed when we drew particle diagrams before. So let's take a look at part 2. So the first one is diffusion of gases. Diffusion, of course, is the spreading out randomly of particles from one container to another. I'm sure you've witnessed diffusion many times. Briefly describe or draw the setup of the demo. Okay, so what I'm going to do is I have a little can here that I have labeled smelly particles. Fortunately, they're good smelling particles, right? It's air freshener. And what I'm going to do is spray air freshener in the center of the lab area. And we're going to observe the diffusion of gases. All right, so I'm just going to shake it up a little bit. And I'm going to spray it right here, middle of the room, right up towards the ceiling. And there we go. And of course, me standing right here next to it, I can smell those particles right away. So what I'm going to do now, I'm going to stand back here. Okay, right now I don't smell them. Stand here a minute. Hopefully, oh no, it won't be a minute. There they are. I smell them already. All right, so let me stand back here, way up towards the front of the room. Wait a little bit. Got my sniffer working here. Don't detect them yet. Cool. There they are. There they are again. So, let's look back here at number 4. Draw a particle diagram showing how the arrangement of particles changed over time from when the can was open until the odor had permeated the room, which it did in a very short amount of time. I'm going to say less than a minute. It was already up towards the front of the room. All right. You've noticed this, I'm sure, when your mom or grandma is cooking a great meal in the kitchen. You're sitting in the living room while watching TV or playing a video game, and all of a sudden you smell that delicious meal which is emanating from the kitchen. All right. The vapor has made its way to the living room. Same thing. All right. So let's take a look at the little diagram here that I have drawn. So if we take a look there, I got to look above my glasses so I can actually read it. So before, I'm showing 2 diagrams. I'm showing the air freshener particles inside the can, and I'm also showing the air particles in the classroom. All right, so first of all, we've got air freshener particles in the can and air molecules in the classroom. After I spray it, now I'm just released air freshener particles in the room, and now as you can see, they have spread from what we just witnessed. They have spread throughout the room. So now we have a mixture of air particles and air freshener particles spread throughout the room. All right. So in number 5, it says, what must matter be like at its simplest level to explain what just happened? Well, number 1, if gas particles started right here and I sprayed them up in the middle of the room and they ended up clear up there in the front of the room by my desk, what do we say? Well, gas particles do what? They move. Simply put, they move. All right. Not only that, do they move in a specific way or do they move randomly? Well, if we'd had a classroom full of kids sitting in here, if you guys had all been here today, you would have noticed that as you were sitting back here closer to the to where I released the air freshener particles, you would have sensed those first, like I was demonstrating. Then as you go more towards the middle of the room, it took a little while longer, and up towards the front of the room a little while longer. And not only that, you would have noticed that it wouldn't have just necessarily been the kids right here in the middle of the room where I sprayed the air freshener, but it was spreading out throughout the room. So gas particles not only move, but they move randomly. All right. It's a random type of motion. All right. The next one, part 3. Diffusion of liquids and hot and cold liquids. Okay, so let me run over here. I'm going to grab a beaker of water that I've been heating on a hot plate back here. Let me go grab that real quick. Okay, And yes, that beaker is fairly warm, so I'm going to set it right there. Move this down a little bit. Okay, see that? Got another beaker of water that's been sitting in an ice bath. So it's, of course, it's quite cold. So let me wipe it off, and we'll put that right there. So there we go. I'm going to scoot this down a little more. There you go, so you can see it. All right, so here's what I'm going to do. I'm going to put a couple of drops of food coloring in each of these beakers. All right. I'm going to put blue food coloring in the cold and red food coloring in the hot. Kind of appropriate there. All right, so I know you can't see me very well. Hello. So I'm going to go ahead and get this one ready. I'm going to try and do them very close together in time. So here is 1, 2, and over here in the hot we have 1, 2. All right, so let's watch. So in number 6 under part 3, briefly describe or draw the setup of the demo. I dropped 2 drops of blue food coloring into the cold water and 2 drops of red food coloring into the hot. And as you can see, they are both diffusing out. They're spreading out, but what do you notice? Pretty obvious difference there. All right. You can actually see the blue food coloring particles are almost like suspended. They're moving, but they're moving quite slowly. But now here we've only been watching for less than a minute, and look at the red particles in the red particles of food dye in the hot water. They have spread out throughout the entire beaker already. All right, and that is certainly not true of the cold ones. This is a really good demo to show the difference in speed of the particles that they're moving. All right, so let me set this aside. Pull this back up here. That's warm. All right, let me set these over here. Like I said, this is a very, very good demo in regards to particle speed and energy. All right, so let's take a look here at number 7. All right, so let's talk about that. So I'm showing the particles of the cold water beaker, and I got 2 different particles in there. I'm showing water particles as well as, if you see the 2 X's there, that's where I dropped the particles of blue food coloring in the center of the beaker. All right, so they're kind of located in the center up near the top. Now, after a minute, what happened? Well, as you can see, the blue particles were mostly still in the center, all right, although they had, of course, spread downward. Gravity, of course, is pulling them down. But they certainly had not spread throughout the entire beaker. In fact, as I look over there now, let's take another look at it. Can you see it there? We still haven't spread throughout the entire beaker. They're still kind of concentrated toward the center, but they at least have moved down to the bottom, and a lot of them have settled down there. Okay. All right, well, now let's look at the particle diagram of the hot one. All right, so there we go. So again, before, the same setup. So the hot water before, and I'm looking right there. So the hot water before, same thing. Sorry, I'm up here. Right there. Sorry about that. We got water particles throughout the beaker, and I dropped the 2 drops of red food coloring in the center. So basically, the before pictures for both cold and hot are the same. But now, after just a few seconds, look at what happened in the hot. Those red food particles had spread throughout the entire beaker very, very quickly. All right. And so I'm showing them spread out a lot more. Okay. Distributed throughout. All right. So number 8 under part 3, relate the impact of energy on the particle motion of matter so that we can explain what happened. So number 1, back up in number 5, we said gas particles move. Well, do liquid particles move? Sure they do. Do they move as quickly as gas particles do? No, they don't. And again, the reason for that is when we talked about particle diagrams, the particles of a liquid are much closer together and have some attractive forces between them, which is restricting their freedom of motion. So they can still slide past one another, as we could see. They can still move, but certainly they can't move as fast. So anyway, so the first point I would say under number 8 is that liquid particles move just like gas particles do. All right. Second point I would say is liquid particles move faster at higher temperatures. All right. That was obvious. Why? Because they have more energy. In that hot water, there's more energy available to those particles than there was in the cold water. And the third thing, which we mentioned just a little bit ago, liquid particles move slower than gas particles do because they have attractive forces between them, and so they're much spaced much closer together, and so their motion then is restricted somewhat. So again, under number 8, number 1, liquid particles move. Number 2, liquid particles move faster at higher temperatures than they do colder ones due to an increase in energy. And number 3, liquid particles move slower than gas particles do because of the spacing is much closer together due to those attractive forces between them. All right. All right. Moving on to part 4, thermal expansion of liquids. All right. So again, you're supposed to watch Eureka video number 19 before you finish up your lesson today. So make sure you do. So let's go to number 10. Briefly describe or draw the setup of the demo. Okay, so here we have basically a test tube with a red liquid in it. It's actually ethanol. You can see that, but I can loosen that up there and rotate it around a little bit. There we go. There it is. So that says ethanol. And then we have another one over here, the blue one. Scoot it around there. Contains water. All right. Now, what I did is I'll just release this. This is like a base, kind of like a thermometer. It looks like a thermometer, doesn't it? Well, this works just like a thermometer. So I'm going to put that glass tube, insert it. There's a glass tube here in the rubber stopper. I'm going to insert it so that it goes in the liquid, and I'm going to tighten that stopper in the test tube. As you can see, the liquid's already started moving up the tube, just like a thermometer does, all right, because of a difference in pressure. All right, now I'm going to do the same thing with the water one, the blue one, and I'm going to tighten the tube so that the pressure inside each of those is about the same. So you can see that they're about the same height initially going up the tube there, all right? So we have an alcohol thermometer, the red one, and we have a water thermometer, the blue one. I'm going to place them both in hot water, and let's watch what happens. Well, we already know that when we place them in hot water, we're going to give the water particles and the alcohol particles more energy, so they're going to move quicker, all right? And as they move quicker, not only within the tube, where else are they going to move quicker? Well, as they're moving quicker down in here, you're going to see a movement up the thermometer, all right, which is exactly how a thermometer works. So I'm going to drop them both down, and you're going to watch very carefully. There's one in, and there's two. All right, so let's watch them. Let's watch. Oh, look here. Look here. The red one's going up pretty fast. The blue one's going up too. Remember, they both started out at the same height. All right, now look. Blue's going up slowly, which is water. The red, the alcohol, is really moving. Look here. Now we're already up here. Just keep watching. Blue's still going up a little bit. Red's going up faster. Remember, these particles have the same amount of energy, all right? They're in the same hot water. Red one's way up here, the alcohol. The blue's moving up too, not nearly as fast. All right, there we go. Boy, the red one's getting way up here now. Still moving up. Blue's still moving up too, but this is like the tortoise versus the hare race, right? The rabbit versus the turtle. I guess slow and steady wins the race, but certainly not here. All right, look at the red one. I'm going to pull this up because if I don't, it's going to go right out the top and I may be already too late. We'll see. So now we're going to cool it down. It should slow down. All right, so take a closer look there, folks. Take a look there. See the difference in the height of those liquids? And remember, those particles had the same amount of energy, all right? Same. But they sure didn't move up the tube at the same speed, did they? So let's talk about that. This is a great demo. So number 11, draw a particle diagram explaining your observations at the particulate level for the alcohol and the water. And then why did the liquid in one tube rise higher than the other? All right, well, let's take a look at that. All right, so here we go. So here's the alcohol thermometer right there before. So I've got the alcohol particles spaced out, all right? And then the alcohol after. Well, what happened? It was still in the liquid phase, right? But as we can see, as they expanded up the tube, those particles were getting spaced farther apart because they originally, almost all of those liquid particles were still in the beaker, or in the test tube, in the test tube. But as we added more energy to them, more and more of them went up into the tube, all right? And then over here with the water, again, we have water before with room temperature, and I have them spread out about the same. And then water after. Well, I didn't change the spacing much because remember, not a whole lot of water particles went up the tube. Some did, obviously, so they should be spaced a little bit farther apart. Hopefully I showed that. But certainly they did not spread out to the degree that the alcohol particles did. So now let's talk about that. In number 12, all right? What property of matter best describes the way a typical alcohol thermometer works? All right. Explain in terms of energy transfer why the alcohol level in the thermometer rises or falls when you place the thermometer in contact with warmer or cooler objects. Well, this is how a thermometer works. All right. As the energy is increased, if you're running a fever, and so your body is warmer. All right. And you put that thermometer in your mouth or under your arm or in your ear, as they do now, I think, or on your forehead. They just keep changing the way they do it. But it's the same effect. All right. As you impart more energy to the alcohol particles in that thermometer, they are moving faster. All right. And as they move faster, they're going to spread out faster, diffuse faster. And in the case of an old-fashioned thermometer in the tube, you can physically see it rise up the tube. Of course, in modern thermometers now, you can't see any of that. It's just digital, which I think kind of boring. You know, I kind of like this better. You can actually see that thing moving. So, you know, I kind of like the old-fashioned thermometers. So why then do we use an alcohol thermometer, which we do, by the way? Thermometers are made with alcohol rather than using a thermometer made of water. All right. Well, let's talk about that. What property of matter best describes the way a thermometer works? Well, what happens is the water and the alcohol don't move up the tube at the same rate of speed because of those intermolecular forces. We talked about liquids have some intermolecular attractions between liquid molecules that keep them closer together than they would be in a gas, as if they were a gas. But now here's the question. Are all intermolecular forces between liquid particles the same? And the answer to that is obviously not, because if they were, then the alcohol particles would have moved up the thermometer tube, the glass tube, at the same speed the water molecules did, and that certainly was not the case. All right, so there must be a difference in those attractive forces between the liquid particles. Okay, so let's kind of sum this up. So under number 12, number 1, liquid particles spread apart faster when the temperature is increased. Again, they have more energy. We saw that with the beakers here a little bit ago. We saw it again with our makeshift thermometers. So liquid particles spread apart faster when their temperature is increased. More energy, particles move faster, they spread out quicker. Number 2, as we very well saw here, different types of liquid particles spread apart at different rates of speed. We saw that right here, right? Different types of liquid particles spread apart at different rates of speed. Think about that. If they spread apart faster, like the alcohol particles did, are they held more or less tightly to each other than the water? Think about it. If they're spreading out faster, all right, then the attractive forces between them must not be as strong. On the other hand, water, the attractive forces between water particles, water molecules, must be a whole lot stronger because they moved up the tube a lot slower, all right? They weren't able to spread apart as quickly. So point number 3 is this: stronger intermolecular forces between liquid particles results in them spreading apart slower, all right? Stronger intermolecular forces between liquid particles results in them spreading apart slower. We mentioned this earlier in another lab we did, but water particles have a very strong attractive force between each other. It's called hydrogen bonding. We're going to learn about that in detail in another unit, but I can tell you this, and now you've witnessed it. Hydrogen bonding is a strong intermolecular attractive force. All right. Obviously, the attractive force between ethanol, which is alcohol that we used here, between alcohol particles is not as strong as the hydrogen bonding intermolecular attractive force that exists between water particles. Okay? So there are three demos that very effectively show some similarities and differences in both gas and liquid particles. All right. So for tomorrow, again, as I looked up at the board, if you haven't already watched those 3 videos, 16, 17, and 18 that are on my calendar and Canvas, you need to watch those. They kind of bring home what we talked about here in these demos. I wanted you to watch them before the demos, but if you haven't, I want you to go back and watch them today. All right. And then you are to watch the 4th video. All right, the 4th one, also located in the same place in Canvas. And then also you are to read and complete the instructions at the top of 2-1 Part B, and using the handout of Part B as your guide, complete questions 1 and 2 only on Part B for tomorrow. All right, 1 and 2 only. So that takes us through today. So this is Mr. Keister signing off. Enjoy your day at home today. Make sure you get all your work done. Get your assignment done for tomorrow. In the meantime, stay safe, everyone, and I will see you tomorrow. So long, everybody.